by the end of the week. If not by the, so if not by Thursday, but certainly probably by the Friday or something around that time. Yeah, so that you have some time to review some questions. But otherwise, in the comprehensive, just 1 second. Otherwise, in the comprehensive exam, it's going to be everything, right? So that's from the beginning. But that said, I would still probably expect, though I haven't really counted, but I would still probably expect something more emphasis on the second part of the course, right? So, but still, 1/3 or something like this, you may still see some questions that you was before, right? Because the final exam, remember that it has a larger weight than the midterm exam. So, and therefore, it will cover both. You have a question?
Yes, it can be the same format as the
Yes, pretty much similar format. Maybe not exactly the same, maybe more questions, but similar format. And you're allowed to bring this one piece of paper where you would write from both sides. Yeah, so let's still have the same rule. But I don't think we need more than this, right? So just I mean, last time I looked, people tried to fit everything. So let's put a limit of just 1 page. Yeah, you can put it double-sided, it's up to you, but just 1 page. Also, if you want to bring a calculator or regular calculator, that's fine. Like just like that last time. One more thing I wanted to mention, I think. In terms of project grading, we also try to grade it by the end of the week or certainly by the beginning of the exam. Once you submit project free, we'll be able to start grading. I think that's pretty much what it is, right? So if you have, I think I don't have anything else to say right now, but yeah. So if you have any questions, please let me know, right? So just post this question on Slack. Or send an email, but better on Slack so that everyone else can see it if they have the same question. So yeah, so by the way, if you have, I mean, I assume that everyone is aware when we have a final exam, so that's in syllabus, right? So yeah, if there's any issue, let me know, and let me know right now, right? Because but I don't think there should be any issue because that's our official schedule. So if there's any conflict with some other course, that's probably we have to ask like the other course why they haven't like exam during the same time, right? So if so unless there is some good reason, let's not shift anything. So if there is any conflict with the other course, try to first check if they can be accommodated with the other course, and before doing anything here, because that's official schedule. So let's stick to that official schedule. Okay. Last time we talked about. We just pretty much stopped here when we discussed file system consistency, and as I said last time, that historically file systems were unsafe, right, in the event of failures. So, and what that means that you can potentially lose the failure can be catastrophic, and you can potentially lose the contents of your root directory. So if you lose the content of your root directory, that's like maybe the worst case scenario. That means you are losing everything that you have in your file system. So losing metadata is very bad. So you want to make sure that at least metadata is in a good shape. I mean, losing one file is bad, like maybe half an hour of your work, right, or something like that. Losing your entire file system where you keep all your files is even, and your system is even worse, right? So that means metadata is very crucial to so to maintain correctly. And again, metadata is not something unimportant, right? So yeah, metadata is not a data, but sometimes metadata is even more important than data. So with the legacy file system such as FAT or FAT32, by the way, do you know what FAT and FAT32 is? So FAT is a file allocation table. That's a legacy file system that was used in DOS and early versions of Windows. I guess nowadays Windows uses NTFS mostly, but still you will see FAT on flash drives or like exFAT, new iteration of that, but still it's pretty much the same idea. Yeah, so so the point is that with this legacy file system you could potentially lose that data right on your file system. So you can run a file system checker that will help. So that can potentially say, oh, that was an orphan file, probably was in the root directory, let me replace, let me put it back, and so on, right? So there is certain things that you can do, but in general, that's not 100% recovery, and anyway, it takes some time to run this tool. You have to scan the entire file system and so on. So there is several approaches to address this problem. One is soft updates, and that kind of relies on the order of file system modifications. It's a very specialized technique, so I will not go into too much details about this, but it exists in BSD operating system, like in their versions of file system, but pretty much that's the only place where it is, and I'm not aware of any other file system. So more general approach is the journaling, right? So we'll talk a little bit about this today. And finally, some newer file systems like rely on log structured approach or copy on write, like you probably heard like LFS, ZFS, BADA or BETAFS, right? But basically it's like some files that's a file system that relies on B trees and so on, right? So there is different approaches like that were implemented recently, but so again, with log structured file systems, there are some other challenges, and I will also briefly mention that. So I would still say that journaling, like you would find that in XT4 or in TFS, so that's still common for regular file systems. Okay, so what is journaling? Fundamentally, right? So journaling was, a special technique in use data-based management systems. Like you would heard, that's pretty much the same ideas that we're gonna talk right now in the context of databases. So you'll hear about transactions, atomicity, and so on. So the idea is that every operation transaction is written into a journal, and that is special on disk place. So like basically on disk, like maybe somewhere in the beginning of your file system partition, you will reserve a place where you would put a log, right? So, and we'll talk about this log. And that is in addition to any metadata or data that you store in a file system. So that basically will contain information that will allow you to basically during failures to either recover or negate the effect of the last transaction, right? So that means if there was something in the process, maybe you're creating a file in the directory, like maybe in a root directory. So, but you will not end up in a situation when there is some orphan file which was created but not placed in any directory, right? So you can either kind of complete that last operation entirely, right? So it means create a file, or completely roll it back. That means, just before the system crashed, I was trying to create a file, and that last transaction is lost. That is often acceptable, right? So if I just before it crashed, I lost that file, that's okay. So I can probably recover that. So sometimes you will see with journaling file system maybe several last modification that happened before your system crashed are gone, right? So you were trying to create a directory. It looked like make your succeeded, but then you don't see that directory after you rebooted your system. Okay, go ahead.
There like a certain amount of time until you delete the previous journals?
Well, you don't, journal is an area, right? So the journal is an area, right? So you don't delete it. It's just kind of permanent area, right, on the file system. But you maybe question transaction, whether we delete that transaction from journal. Yes, so so we will do remove it periodically. So I'll get to that in a moment. Okay, good question. Any other questions? So there are fundamentally three things that we need to achieve in file system, in journal file systems. Atomicity of operations. So atomic, something that we have already heard in the context of concurrency. That means something that shouldn't be like indivisible, right? So something that cannot be divided further, right? I mean, again, this is like atom is not something that cannot be, I mean, atom can be divided further, but in the context of computer science, atomicity means like something that is indivisible, right? From its original, I think, Greek meaning, right? Yeah, so you I mean, at some point people believe that atom cannot be divided further, right? So this is why they called it atom. Yeah, so but that's what it is. So we want to make sure that all operations are indivisible. So either I create that file or not create it at all, because I don't want to end up in a situation when I have some orphan file or that kind of in a limbo state that is not placed in any directory and so on. Or like, let's say I'm writing 2 megabytes of data. I don't want to end up in a situation where I wrote only like 1 megabyte of data. So I want to make sure I either write this 2 megabytes or I don't write it at all. Then there is file system consistency. So that is something that we will, that's a property of file system. So we want to make sure that the file system itself will not get corrupted, even during failures. So now durability of changes is something that, I want to make sure that eventually they're not going to be lost, in the event of failure, right? So all these changes that I'm making are going to be preserved, right? That's kind of partially related to consistency and atomicity, but sometimes it's viewed as a separate property. Yeah, so let me discuss what kind of approaches we can have. So there are two major approaches that you can take. So one is a logical journaling. So that means you will represent all changes as some sort of trivial high-level modifications. So you will say, okay, I'm creating that file in that directory. I create file of that size or that size and so on, right? So it's a high-level modifications that you want to kind of record, right? But recovery in this case is kind of complicated. It also has to really know about the how this file system is organized, so it's not necessarily trivial. So now physical journaling, like such as one that you find in XT4 in Linux file system, right? So will represent transaction as series or block modification. So let me give you an example. So what effectively happens is that you have some area in your file system partition like called journal, right, or log. And that's maybe the real like place like where you store data, metadata, whatever it is. So what will happen is that, let's say I want to write this block 1, but before I write block 1, it will go to the journal buffer. So it will kind of be duplicated here. So maybe I will write block 10, that will be duplicated here, and so on. So physical journaling means, like in logical, I will kind of say, oh, I want to modify block 1 or block 10 is this kind of change and so on. With physical, I'm gonna say I don't care what operation it is, whether it's create directory, you know, like create file, doesn't matter, right? So I'm just gonna keep whatever this block I need to update it, I'm gonna keep the copy here. So I'm just blindly copying this metadata that I'm updating without even looking what I'm updating. So that way I can always recover from the copy that I have here. So let's talk about how we can recover. So in that sense, it's very low level. It doesn't matter what operations you do. You can implement any operation like this, but you just need to copy the entire content of that block in the corresponding log area. So by the way, in terms of journaling, you can have metadata only, you know, sometimes metadata and data, and sometimes combined approaches. I mean, certainly want to do metadata, that's for sure. You know, if you lose your root directory, it's catastrophic failure. You don't want to do that, right? Like losing data in one file and have some inconsistent data is bad. File is corrupted now and so on, right? But we can probably live with this. Metadata is much harder problem, right? So we have to make sure at least metadata is in correct shape. Yeah, now like I have a list of files, overall structure is fine, but when I look at this file is corrupted because of power loss, right? So maybe it's also not great, but sometimes it's still acceptable. So sometimes it's not acceptable, and therefore you want to journal both data and metadata. But obviously there is an overhead for this because data is much larger than metadata. And you, as I said, have to duplicate that in the journal area, and that is a problem. So if effectively, if you're gonna do data and metadata, you have to double number of writes that you need to do. Finally, there is some hybrid approaches when you would do some metadata modification first. Well, when you do data modifications first, and then you would order them such that you would kind of change metadata for journal later. I think XT4 supports this model. So it's kind of mixed model where you don't actually do journaling for data, but you still use some ordering techniques to make sure that you don't end up with corrupted data. Or at least most of the time you will not end up with corrupted data. Yeah, so that is an approach that you can also use. So in terms of login, right? So there is so-called write-ahead login, right? So the idea here is that all modifications are written to the journal buffer before they actually written to the target disk location. So this is a target disk location, V1, V10, and so on. So I'm not allowed to change them until I finish writing this transaction here in the journal buffer. So if I'm modifying some directory and it requires modifying V1, V10, V12, you know, and so on, I have to make sure that I'm reading all these blocks here in the journal area. And only after this, I'm going to go and write V1, V10, V13 in the target location. So that is what write-ahead login is. So, but in the event of failure, we have 2 scenarios. So the journal buffer, this one, right? contains all modification made during the last transaction. So it contains B1, B10, B13, whatever, right? So that means the end marker, so that may be the beginning mark of the transaction, that's the end marker, like journal end. Like end marker is written, so I know where the transaction ends. Journal buffer is fully written. So that means I can replay this last transaction. I can just go back and whenever I mount the file system, I can just go write B1 to B1, B10 to B10, and so on, right? Because I have an exact copy here, I will write the target location in the head of before this blocks, and we'll pretty much replay that transaction. Now the question is, and that actually will take care of the case, because as I said, you'll write the marker. Only after this, you're allowed to change target locations, B1, B10, and so on. So you may end up in a situation when B1 is written, but B10 is not written. Or maybe vice versa, B10 is not written, but B1 is not written. But that's not an issue because you have all copies for data blocks here in your journal. So you can just go and replace all of them. Just blindly go and replace B1 to B1, B10 to B10. Some of them will be overwritten with the same data, some will be written with new data, doesn't matter. Maybe everything was written correctly to the disk. Maybe you got lucky, but doesn't matter because we're just gonna overwrite with the same data from the journal area. Because we don't know for sure whether all data was written for the last transaction. We have to replay it. So now, while I'm replaying, my file system can again crash, maybe system will reboot during system startup for whatever reason, some other issues. So while I'm mounting file system, I can also have a power loss. So that means I'm not gonna update anything in the journal buffer. I'm not gonna clean up that space. So I will try when I mount again, I will replay it again and again and again until it finally mounting succeeds. And then at that point, I can clean up the journal area. So now the other issue, the other case is that journal end is not written. But then when the journal end is not written, B1 and B10 is not written. That because I'm only allowed to run write B1 and B10 after journal end. So that means what it means. That means that the journal end marker is not written yet, and we don't know whether this transaction is complete or not, but basically we treat it as garbage. So because we may not have all blocks that we need to modify, so we're gonna discard this transaction. And there is no problem because the target location on the disk were not yet modified. So the file system does not have that directory that you're trying to create when the system crashed. So there is no damage made, right? So because only journal contained that modification. Yeah, so it's also possible to keep both new and old versions of the blocks whenever you modify in the journal area, but typically in practice that's unnecessary because you only want to completely negate unsuccessful operations. If it was a successful operation, I guess in the context of file system, like if you successfully create a directory, we don't want to cancel that, right? I mean, maybe in context of databases, it's useful to be able to roll back some transactions that even if they were successful. But if you successfully created a directory in file system, we don't want to roll it back. So and therefore, typically we only keep new versions. So we will say in the journal area, we'll just write a new version of block 1 or block 10. So we can also batch changes. Maybe in block 10 is changed multiple times. And in journal area, we can just write it once, block 10, and maybe a multiple transaction can be batch. Maybe you created 10,000 files in a directory. So maybe you can combine it in one large transaction. and then pretty much, I mean, maybe it's not a good idea because I guess if we created 10,000 files, that will all be lost, right? So if it's just one transaction. But on the other hand, it depends on timing, right? So if it was created by some script, like a last minute before the crash, it's not such a big deal. It's like more like on the other hand, if it was like representing your work over the week, that's not good, right? So you want to make sure that I guess after some time, maybe periodically, you flash transaction on the hard disk, right? So maybe losing 1 minute is okay, like losing a week of work is not okay. Yeah, so you want to periodically do that. I think I mentioned last time I was using some buggy operating system and there was like I got a habit of running sync because it was not flashing to the disk automatically. So I mean, everything would stay there and like would batch them one large transaction, which will be lost after the crash. Yeah, the file system was still sometimes. I mean, the file system also had some bugs, but so it was still kind of boot next time, but all changes are lost, right? So that you want to make sure you don't have that situation. So you want to periodically flash, and like I mean, typically in Linux, I think it periodically would flash that. I think one every 30 seconds or something like that, right? So some periodically it would flash that to the disk. So now, how do we write this transaction to a journal buffer? So that's a circular buffer. I think we already talked about circular buffer in the context of memory, and a somewhat similar idea is used in the context of file system. So we're gonna keep writing to this buffer, but at the end of the day, we're gonna reach the end of this buffer. So then we'll go back to the beginning and continue writing in a circular fashion, right? So we will pretty much use this mod operation, like a modular division operation, to go back to the beginning. So now, at that point, we will find some older transactions here. And we can, make sure that they're fully flashed to disk and then discard them. So we can, like in the beginning, there will be some older transactions. So we can clean them up and, recycle that space for a new transaction. So cleaning up means moving journal start. And journal end, so journal starts points to the beginning of the first transaction and journal end points to the last transaction. So it can be like this, journal start is here and journal end is here. That means I started from here, like wrapping around and continuing here. Okay.
Did you have a situation where the transaction size is larger than the journal?
Yeah, that's actually a very good question. Yes, you can. That's actually in some file systems you can, and that's very unfortunate. But I think this is actually rarely talk in the literature. But in general, yes, you can potentially. I've seen those cases, and to be honest, there is no good solution for that, right? But yeah, because if you cannot fit it in a journal buffer, then those kind of corner cases, in that cases you will not be able to guarantee atomicity or consistency or anything else. You have to be able to fit at least one transaction in journal area. So I guess there is no good solution for that, but I guess those cases are extremely rare, I think, and they're very kind of corner cases. So when you create a directory, that's going to modify a few blocks. When you're gonna create a file, even if it's a large file, right? So that's still going to be a few blocks that you allocated. But yeah, I agree that sometimes it will not fit. And I've seen some cases like that, but but let's just kind of put those corner cases aside. I mean, everything is kind of always good in theory. In practice, there are some exceptions. Okay. Yeah. So. yeah, so that's pretty much what we have in the circle buffer. We'll keep a header which will say what blocks we need to modify in the target locations, and then block 1 up to block n, the next transaction, finally journal end. As I said, maybe the last transaction that we are writing is going to be after journal end, and we haven't modified journal end yet until we complete. So if there is some failure, we will treat it as garbage. So because a last transaction was not fully complete, so we just pretend that this transaction doesn't exist. And it was not written to the target location, so that's still fine. So as I said, if there is crash, we'll just go and replay the journal entry. So typically a file system has some sort of super block, right? And there are some flags, like the file super block will contain information about the root directory, other things. We'll also have a file flag that will mark like file system as dirty when you mount it, and as clean when you unmount it. So if, like, let's say if next time it sees that it's dirty, that means it was not unmounted properly, and therefore you have to replay the journal buffer and look at it. Just go to the journal start and journal end and replay it. But the question is now journal start and journal end. How do we make sure that these things are atomic? Because eventually that's all kind of relying on the fact that journal start, journal end can be changed atomically. I mean, the area is fine, right? So if I didn't update journal end, then that's the like last stuff is going to be like at the end of the buffer will be treated as garbage. But how do I make sure journal start and journal end is updated atomically? Well, but there is no logs. But here we can basically rely on the fact that we unit of data, like we have 512 byte sector that we write in superblock. Hopefully when the hard disk writes this 512 bytes, it's not going to be like half updated or something like this. So typically sectors are either fully updated or not updated at all, right? So we eventually going to rely on that, right? So journal start, journal end will probably go on a super block, and that super block maybe is 512 byte sector, which either updated or not updated at all. Yeah, so the transaction must be proceeded in the order, right? So like first start all the transactions, then newer transaction. So why is that important? Why is that important? So why do we need to proceed in that order? Well, the reason for that is let's say I have B1, B10, transaction 1, then maybe transaction 2, B12, B1, and so on, right? So that's my journal area. And then I have target disk location. So I have B1 updated here, B10 updated here, B12 updated here. Right, so in the transaction, when I replay it, I'm gonna start from the beginning, from the journal start. So I'm gonna go and write B1, but who knows, B1 maybe contains version 2 already. So that's version 2 and that's version 1. Because maybe crash happened here, and this is journal end, right? We are already able to write journal end. So after this, it's garbage, right? Maybe there was version 3, but it's it's not there yet. So maybe B1 contains version 2, but that's not an issue because I'm gonna write version 1 here. So temporarily, I'm gonna replace it with version 1. with an older version. But then eventually remember that I have to replay all transactions that I have. And I have to replay them in the right order. Transaction one only after this transaction two and so on. So then eventually it's going to be replaced to version two again. So even if even I have multiple versions, I should still be okay at the end. And remember, if there's version 3 of block 1 here in the garbage area, that is not written yet to the disk because we are only allowed to write to the disk when we finish journal end. So once we finished everything in journal buffer, like any new transaction that was in progress there, is not written to the disk yet. So we're just discarding that T3. If it exists, maybe it doesn't even exist at all, right? But if it exists, we're gonna discard it. And there is no version 3 because it was never written to the disk. So it's important to do it in the right order. Okay, so different transaction may modify the same block because remember, it may be just the same root directory that you updated, the same inode. So, so you create maybe 10,000 files, and, they're going to update the same block over and over again. So as I said, recovery procedure can fail, but that's not an issue because until we can replay that as many times as we want, right? Remember that we are not going to allow a mounting until we finish replaying. So mount will not return until you successfully finish replaying. And sometimes people may allow to do it a read-only mount, but certainly don't want to mount file system for writing if you haven't finished recovery, because then you can create damage right to the file system. So you want to finish replaying first. But even for reading, that's not acceptable because some of this metadata is completely inconsistent. So you have to finish replaying the journal buffer first. So sometimes you will do batching. Sometimes you might maybe batch. Like if you create 10,000 files, as I said, maybe you're going to modify the same block over and over again. You want to batch that in one transaction. But again, there is certain limit. I mean, in terms of timing, it's important to limit how much you are batching because you don't want to lose. I mean, because you can say, all work I did over the past week is just one transaction, right? Which I have lost during the power crash. That's not acceptable, right? So I think there is some time, there should be some reasonable time limit for that. Any questions so far? Yeah, so this is about journaling, right? So the other alternative is log structured file system, which I briefly mentioned already, right? So, but log structured file system is effectively treating your entire log area as a file system. So it's kind of more radical approach. It's saying, your log is your file system, right? Pretty much, right? So it's an interesting idea, and I think it's already kind of widely used in some, certain applications. But XT4 is not log structured file system, but still there's some other examples, right? But the advantage of that, what is the disadvantage? We have to duplicate these blocks of journaling, right? We have to write the same block to the journal area. So ideally, we want to avoid it. Ideally, we want to avoid this duplication. So if we kind of treat it as the log structure as just one copy, that's maybe acceptable. But then the problem is you have to kind of garbage collect some previous stuff in front of you, and that's not trivial, right? So there will be garbage collection issues for log structured file system, which you don't have for journaling. For journaling, you can remove a file, just update your journal area, and that's it. For log structure, to remove some old data, you have to do garbage collection in the log area. So that's not easy. That's not to say it's not easy. It's probably, I guess, fundamentally easy, but but it's an expensive operation, right? It's like, you know, when if you ever use Java, maybe sometimes you rely on garbage collection, can be sometimes feeling sluggish, right? So the system is a little bit sluggish, right? When you use manual reclamation, like manual memory management, like in C, whenever you're done, you just deallocate, you know, then you allocate again and so on, right? I mean, there is no good answer what is better. Sometimes it's this one approach is better, and sometimes the other approach is better. Uh, yeah, I guess that analogy we can make. Yeah, so, and not to mention that so some real-time system garbage collection is not a good idea because I don't necessarily know how much time it will take. And you know, for allocation or deallocation, right, with manual memory management, I can know for sure, at least I can estimate like some upper bounds, how much time it will take to do allocation and deallocation in good systems, right? With garbage collection, you know, maybe you need to clean up your entire memory. Who knows, right? So, like, what kind of bound you have there? So again, it's not. I mean, some still, I guess, if you can put some bound there. It's. I shouldn't say that you cannot find any bound, but that bound is going to be probably larger than with manual management. And the same thing here, right? So if you may win or like with garbage collection sometimes, and like maybe that file system will be overall faster, but maybe in some corner cases it will be also slower, right? Okay, that's just, you know, that's going to be beyond the scope of this course, so you can probably read a little bit about this in textbook if you are interested, just to have some general idea that there is some alternatives to journaling as well. Okay, so what is, let's go back to the file system interface. And fundamentally, what is a file? File is just a named piece of storage. By the way, nowadays what we treat like files, we treat a file just some sort of collection of bytes. You know, it doesn't have any type or anything, right? So it's just, you know, bunch of bytes and that's it, right? So that's what a file is. I mean, historically, it's not exactly the same. Like historically, people viewed files differently, right? So there were some types and also, but you know, modern operating systems, it's just pretty much a collection of bytes and that's it. So what kind of file operations you have? Well, there is, remember that there is a system calls that we have, and libc supports pretty much direct access to system calls. I mean, of course, they implemented through functions, but they are pretty much translated directly to the corresponding system calls. So you have read, write system calls, open, close, and so on. So remember that I can just read and write to a file, and but that's just a really low-level interface. In fact, like if I'm using printf, the printf function, that's going to be translated to the write system call. I think we looked some time ago at that. So it will just write to the file descriptor one, which is standard output, and you know, so that's what printf is. But then you also have buffered versions of these functions like fread, fwrite, you know, fopen, fclose, and you know that basically that exists pretty much in every language, like in C, Java, anywhere you will see that you have that kind of buffered interface. So that allows you to use some buffering, so you don't necessarily need to, you know, write 2 bytes or like 4 kilobytes, so that can be stored in some intermediate user space buffer to make things faster. And again, like printf will also be definitely buffered. It's also a high level function and will also get translated to write system call. So it's not just fwrite, like fprintf is also the same thing and so on. So what is a file descriptor? Well, the file descriptor identifies a file And remember there are 3 standard file descriptors, 0 is standard inputs, 1 is standard output, and 2 is standard error. So those are already opened in every program by default, right? So you can use them, and if like remember that if you use printf, that's just write to file descriptor 1. And you know, why do we need let me ask a question, right? So like why do we need a file descriptor? So eventually remember that in the kernel that's going to be some inode that I'm opening and so on. Why do you need this integer number? Okay. Yeah, that's fine. Yeah, so I can uniquely, yeah, definitely that uniquely identifies the file. But why is it file descriptor? Why can't I just keep some file pointer, like to maybe to the open inode? Because that will also uniquely identify, I guess, right? So like, okay, go ahead. Well, no, I guess. Okay, let me put it this way. Yeah, let's say I have a like I have a file descriptor, but I also have a file description in the voice kernel, right? So maybe I have an open file, and that like maybe file star structure which contains like a reference to inode and so on, right? Um, and that file star is probably unique, right? So it maybe has some pointer. At least this you pointer unique as long as this file is open, right? Uh, so why can't I just, refer to that file star pointer from user space? Why do I need to have that integers? So why can't I just take that pointer there and use it? Any guesses? Okay.
Basically, move the file.
Well, you move a file, but no, but this is not a concern because it's like file would roughly represent an inode, and moving a file is basically removing the sign from one directory and inserting to another directory. But the files that are already opened, they're kind of, they'll be, already opened, right? So it's a good question, but it's just semantics is that if you move the file, it's already open, then you can still access it. So sometimes, for example, I mean, this is actually different semantics in Windows and Linux. In Windows, if I'm trying to delete a file which is opened and used by some program, that will not allow me to delete it. It will say that files cannot be deleted. In Linux, I delete a file that is opened by some program that will still allow me to do that. But that file that is already open is kind of limbo state. So it's no longer exists in any directory. But so periodically I'm writing this file to nowhere. If I do some changes, that will not go anywhere, right? So, but they will eventually be discarded once I close that file. But so it just this file becomes invisible, so to say, right? But aside from that, file pointers. Remember that file pointers. Well, I should say not aside from that, but the problem that we want to solve is that file pointers are not that are passed from user space program are not trustworthy, because user program may pretend that it opens some other file which really was opened in some different process. Maybe that process was running with like root permissions and your process is running without root permissions. So maybe some system administrator was opening one file and you opening like you don't have that privileges to access that file. So you just happen to know that pointer in memory and now you can access that file. Yeah, that's not acceptable. So you don't want to allow that. So again, that because we cannot trust any user program, and then it's much easier to check file descriptors. So now for each process, you're gonna have a file descriptor table, and that's typically a small table like, default is 1024 file descriptors. I mean, you can increase it, but the default is 1K, right? So it's going to be go from 0 to the 1023. And that's a relatively small array that you need to keep, and you can easily translate the corresponding index to the corresponding file description. And that table is kept inside the OS kernel, so the user has no control of that table. So the user can only have this number, and then the kernel is going to go, okay, you specified file descriptor 10. Let me check whether you have that entry 10. Okay, you have that entry 10 that corresponds to that pointer. Or maybe you don't have that 10, right? The 10 is not open file. Then I'm saying that the file descriptor is incorrect. So it's easy to check the file descriptor. It's easy to check it that way because when it's a small number. So, okay. Any questions about file descriptors? So again, it's just a table. Each process is gonna have a table which will translate a file descriptor to a file description. And that table is only accessible from the OS kernel, not accessible from user space. Okay. Process file. Yeah, so each process opens, multiple threads in the same process, you're gonna share the same file descriptors. But different processors will have different file descriptors. Now, it may potentially refer to the same open file from multiple processes, but that's a different story, right? So multiple processes can open the same file. They may have different file descriptors, which correspond to the same file description, but that's a different story. Yeah, so that the bottom line here, you want to have that translation specific to your process and something that is easy to check. Because checking 1024 file descriptors is easier. Checking arbitrary pointer is much harder. Yeah, so what is the purpose of file systems? Well, the general purpose, of course, is to make storage usable, because otherwise you just don't have any structure, you don't have any directories, you don't have any files. Just if you treat your storage as just large chunk of data, there's no structure to that. So that's the first thing, right? So you want to make track file information, metadata. The other thing is you want to map files to blocks. So similar to page tables, virtual address space, for files, we have file offsets, like maybe file offset 0, file offset, 1024, 2048, and so on, right? Those should correspond to some disk locations. What file thinks is 0 doesn't necessarily mean it's stored on the disk location 0. So there is somewhat similar translation that happens in the file system. So we want to translate file location to the disk location. So we want to map files to blocks. And finally, we want to track and allocate free blocks. So that means some files will get removed. So we want to keep track of what blocks are free so that we can use them for new files and so on. So that is kind of similar to what we did in memory allocation, but now that's in the context of storage rather than memory. So what metadata do we have? So first of all, metadata is something that is not actual data. For example, for journaling, as I mentioned, our goal is to make sure that at least metadata is safe, right? I mean, data is okay also if I can make sure that if I can allow journaling both data and metadata, that's great. But at least I want to make sure that metadata is correct. And likewise, maybe there is some approaches in XT4, like they would kind of combine. They would make sure that data is first reading, and then only after this I update metadata. So there might be some ordering techniques. But metadata is basically something that is not the actual data. So what are the examples? File name, right? So that's metadata. Size of the file, timestamps, file owner, file permissions, information about blocks, right? So where those file data is located. So it's similar to like page table, right? So we have like that page table as some sort of, in the context of file system, it should be stored somewhere. So that's also metadata. Right? So some of this metadata, or most of this metadata, is part of the inode. But some metadata, like file name, is not part of the inode typically. So why is file name is not part of the inode? And where do we keep file name? Any ideas why we cannot store file name in inode? Yeah, so okay, go ahead. Well, size of the file is a separate thing, right? So size of file is actually kept in the inode. Oh, file name. Well, I guess it's not the major problem. Yeah, it's true that maybe file name is very long, right? And I don't know if I have space in inode for that. But inode, I can probably make inode. I mean, what is the file name? Maybe 255 bytes or whatever, 256 bytes. Inode, I can just make inode a little larger. I don't know, right? There is different approaches. I mean, certainly I can make inode at least one block. That's not a concern. Like 4 kilobytes or whatever, right? So we should be able to feed that file name. But is there any? But it's a good point. But it's not the main reason, right? So what is another? Okay, go ahead.
Because we need the file name to access inode.
Well, but to access inode, yeah, it's a good point. But yeah, yeah. So it's true, right? So, but yeah, and that I guess one of also reasons, right? Why we need file name outside. But is there any other reason why it doesn't make sense to keep file name in an inode? Well, the reason for that, remember, like file, or at least why I mean, yeah, so to access file, yeah, you need the file name, of course, right? Because to reach the inode, that's a good point. But why can't I have an inode in general, right? So the problem is there might be multiple paths to the same file, fundamentally. Like, when can it happen? Well, with symbolic links, it's easy, right? So symbolic link is a special file which contains a path to another file, right? So that's, I guess that doesn't count too much, right? But then there is so-called hard link that you have in the system. And a hard link is basically just an alternative name for the same file. So it can be placed in the different directory, but it's gonna point to the same inode. So that can be a completely different file name, completely different file path, but just, but the same fundamental file, the same permissions with everything, the same size. Everything is the same, but just in a different directory. So if you ever try to create a hard link, you can see that, right? Yeah, so symbolic, again, it's not a symbolic link. Symbolic link is a special file which contains a path to another file. But hard link is not a separate file. Hard link is the same file, just an alternative name with alternative name. So therefore, it doesn't make sense to keep file name inside the inode. And the other good reason that you mentioned is that we have to reach that file path, right? So somehow. So how do we reach that file? How do we reach that inode? We need to keep information about the file name in the directory. So in the directory, what we will have, we're gonna have file name and the corresponding inode number, right? So at each point, so remember, directory is just a special file which contains information about other files, including directories, right? So it basically, fundamentally, each directory is fundamentally each directory is just a list of files, like maybe ls 1, 2, 3, Bob 4, 4, 5, 6, and so on, right? That's inode number and the directory entry name, which is file name. So let's say that is /home contains that information. So that file home directly contains that information. And maybe I have home ls and so on, right? So I have information about ls. I go to that directory. In that directory, I'm gonna see other entries. Okay. So by the way, why is that? Yeah, let me get back in a second. Okay, that's pretty much what the directory is, right? So now let's look at file permissions, right? So file permissions is just a bunch of bits, like we'll say like on read, allowed, not allowed, on write, allowed, not allowed. So whatever you do, change mode. So that's basically translates to this 9 bits. Right, so and that you can just keep that as the integer number inside the inode. So 16-bit integer is more than enough for that. So you'll just pretty much keep that information about permission. Now there is also user ID and group ID also stored in inode. So whenever you open a file, you can compare whether whether you have permission to open that file, and if you don't, of course it will prevent opening that file. So now, of course, when you open a file with checks permissions, doesn't mean that you cannot open that file, read that file in general, right? Maybe if you boot from flash stick, flash drive, we have like root permissions, you can access that file system, of course, right? Unless it's encrypted. So if it's encrypted, then of course you have to know the key and so on. But that relies on the operating system, right? So on the current operating system. So I mean, on my local machine, I'm entering the password, right? So the kernel either allows me to run as this user or not, right? So if I'm not running as this user, then the kernel will prevent access to that file. But I have to have encryption to make sure that it's actually safe, right? So because if someone gets my computer, unplugs the hard disk, they can do whatever they want, right? Okay, go ahead. Yeah, well, what inode, yeah, typically you want to encrypt inode as well, right? Because you don't want to reveal metadata, right, as well. How do you know the size? Well, again, it depends on the granularity of encryption. Sometimes you just encrypt the entire partition with one key, and that's like you don't have any access. You cannot even access to the file system without that, right? Sometimes you will just maybe encrypt data. So it just depends on the granularity, right? There are different approaches. It's a good point. Sometimes you will encrypt the partition. Sometimes you will encrypt the entire disk, right? Okay, so what else do we have? So mapping files to blocks. So the simple approach would be to have a linked list of data blocks, right? So which is not good, because if I, like again, it's a legacy approach, just saying, okay, that block corresponds to that one, because I need to have random access in the file. List is always bad because I need to linearly scan it and find the place and so on. That's bad. So have an index table is better, right? So it's somewhat like a page table, but with somewhat better flexibility, right? So for example, you have direct blocks. This is where you have, let's say it's maybe 16 blocks, 16 mappings you can directly keep in the inode. So you will say block zero and file offset will correspond to that block and so on, right? Maybe after 16 blocks, like that's already like a lot of space, right? That's more than 100 bytes already, right? So you want to keep a indirect block. So indirect block is like level, just one level page table, right? So you just have one block which stores information about other blocks. So that means, like, let's say you have 4 kilobyte block size and 8 byte address. So that's going to be 512 mappings that you can keep there. So 512 more you can keep in indirect blocks. Then the problem is that, your file becomes larger. 512 is like, what? It's like still maybe you want to keep megabytes of data now, right? So maybe you want to use double indirect. So that's going to be like 2-level page table. And then, finally for very large files, maybe you want to have triple indirect. So that's 3-level page table, right? So you're going to create more and more mappings. So it's a little more flexible depending on the file size. It will kind of increase. So it will go from direct blocks for smaller files and then increase it to triple indirects for very large files. So you'll typically use all levels like direct, indirect, double indirect, and final triple indirect. So it's not like direct or triple indirect, right? So it's you still using all of them. First 16 mappings indirect, another 512 and the indirect and so on. Yeah, what time is it? Okay. Just last in tracking and allocating 3 blocks. So the simple approach would be to keep a free list like this, right? You have a block, it's free, pointing to another block which is free, and so on, right? So maybe this is 8 bytes, this is 4 kilobytes. So you just recycle the space of the block itself to link to another place. Just like something we did for memory allocator. But this is a little bit wasteful because if I need to, let's say, allocate 1,000 blocks, that's bad, right? So I have to iterate through all these blocks to find where they are, right? I have to read the 1,000 blocks. So an alternative would be to use some sort of bitmap. So that bitmap can be stored before the blocks on the disk. And each bit will say this block is available free, right? This block is allocated of free, and so on. So let's say I have 4 kilobyte bitmap block. So that's 4096. Each byte is 8 bits, right? So 4096 by 8, 32,768, right? So more than 32,000 blocks can be referred, can be referred from one bitmap block. That is good, right? So because I can immediately allocate by just reading one block, I can immediately say what blocks are free or what are not free, and I can allocate up to like 32,768 blocks by just updating one block. So instead of iterating 32,000 blocks with a long list, I can just read one block and say, now this block is allocated. This block is also allocated. I just need to modify this one. Just modifying one bitmap block is already enough, right? Yeah, let's stop here and talk a little more next lecture. So for the last lecture we're gonna have on next week, again, I will post some sample exams maybe by the end of the week. So also those who were late today, I just want to say that for